Tonight, we're going to talk about something that quietly unsettles astronomers around the world. Not because it's dangerous, and not because it belongs to science fiction, but because it doesn't make sense. These are the kinds of discoveries that don't trigger panic. They trigger confusion. The kind of confusion that keeps scientists staring at data long after the observatory lights are off, rereading numbers, recalibrating instruments, and asking the same uncomfortable question over and over again. How is this possible? Out there in the universe, we've observed things that seem to ignore the rules we thought were fundamental. Objects that behave in ways our equations don't predict. Signals that appear once and vanish forever. Structures so vast they shouldn't have had enough time to form since the beginning of the cosmos. And the most important thing to understand from the very start is this. These are not ideas, guesses, or speculative theories. These are real observations. Measured, recorded, verified by multiple instruments, and acknowledged by the scientific community, even when no explanation exists. Over the last few decades, astronomy has entered a strange new era. As our telescopes became more sensitive, as we learned to observe the universe in radio waves, infrared light, X-rays, and even gravitational waves, something unexpected happened. Instead of everything becoming clearer and more orderly, the universe became stranger. Every improvement in technology peeled back another layer and revealed anomalies hiding underneath, things we simply couldn't see before. It's like upgrading a microscope and discovering that what looked smooth is actually chaotic and full of structure. This video is a journey through those discoveries, a guided tour of genuine cosmic oddities that challenge our understanding of physics, cosmology, and even time itself. Some of them are famous. Others are barely known outside academic circles, but all of them share one thing in common. No one fully understands them yet. And that's not a failure of science, it's how science works at the frontier. When observations stop fitting our models, it means we're standing at the edge of something new. Along the way, you'll see how better instruments don't just give us better answers, they give us better questions. They reveal phenomena we didn't even know to look for. Before we dive in, if you enjoy deep explorations like this, stories where the universe refuses to behave the way we expect, consider liking the video or subscribing. It's a small gesture, but it helps keep these long-form explorations possible. Now, let's begin, because some of the strangest things we've ever discovered are already out there, and they're waiting to be understood. The first stop on this journey takes us back to a very specific moment in time, a moment so brief and so strange that it still echoes through astronomy nearly half a century later. On August 15, 1977, a radio telescope known as the Big Ear was quietly doing what it did every day, scanning the sky for faint whispers from the cosmos. The telescope was operated by Ohio State University and was part of a long-running scientific effort called SETI, a project designed to search for artificial radio signals that might indicate intelligent life beyond Earth. Most of the time, this work was deeply uneventful. The data consisted almost entirely of background noise, the natural static produced by stars, galaxies, and the countless energetic processes that fill the universe. Day after day, page after page, nothing stood out. Until one day, something did. A volunteer researcher named Jerry Amon was reviewing a printout of the telescope's data when he noticed a sequence of numbers that immediately looked wrong. Not broken, not glitched, just wrong in a way that made his brain stop. The signal was far stronger than the surrounding noise, rising smoothly from nothing, peaking, and then fading away again. In the margin of the printout, almost instinctively, he circled the numbers and wrote a single word. Wow. That spontaneous reaction is the only reason the signal is remembered by that name today. The wow. Signal, as it came to be known, lasted exactly 72 seconds. That duration wasn't arbitrary. It matched the amount of time the Big Ear telescope could observe a single point in the sky as Earth rotated. During those 72 seconds, the signal was about 30 times stronger than the background noise, an extraordinary spike in an otherwise quiet data set. Even more intriguing was its frequency. The signal appeared at around 1420 megahertz, almost exactly at the hydrogen line. This frequency is special because hydrogen is the most abundant element in the universe, and the hydrogen line is a natural radio emission produced when hydrogen atoms flip their electron spin. Because of its universality, astronomers have long considered it a kind of cosmic reference frequency. If an intelligent civilization wanted to transmit a signal that other civilizations might notice, choosing a frequency tied to hydrogen would make a certain kind of sense. It's a frequency any technologically advanced society studying radio astronomy would likely recognize. But the story gets stranger. The Big Ear telescope used two receivers to scan the same region of sky, separated by a short time interval. A genuine celestial signal should appear in both receivers as Earth's rotation carried the telescope's view across the source. The wow. Signal appeared clearly in the first receiver, but it never appeared in the second. This told astronomers something crucial. Whatever produced the signal was not a steady source. It was transient, switching on and off in less than 3 minutes, with the best estimate being those original 72 seconds. After that, it was gone. Over the decades that followed, astronomers returned to that exact region of the sky again and again. They used more sensitive instruments. They listened at the same frequency and at nearby frequencies. They searched for any hint of repetition. Nothing. The signal never came back. This single fact is what transforms the wow signal from an intriguing anomaly into a lasting mystery. In science, repetition is everything. If a phenomenon can be observed again, it can be studied, tested, and eventually explained. A one-time event offers no such luxury. With only one data point, explanations become slippery. Naturally, the most attention-grabbing possibility was that the signal might have been artificial, perhaps a transmission from an extraterrestrial civilization. The narrow-band nature of the signal strongly supports this idea at first glance. Natural astrophysical sources tend to emit radio waves across a broad range of frequencies, producing messy, noisy signals. The wow signal was sharply confined to a very narrow slice of the radio spectrum, exactly the kind of precision you'd expect from a deliberate transmitter. But extraordinary claims demand extraordinary evidence, and one unexplained signal is not enough. Scientists are trained to exhaust every natural explanation before entertaining something so profound. One proposal suggested that the signal came from a comet. As comets move through space, their hydrogen-rich clouds can interact with the solar wind and emit radio waves, including near the hydrogen line. In 2016, a researcher proposed that one or more comets may have been passing through the region of sky where the signal was detected. At first, this seemed promising. It offered a natural source that didn't require new physics or alien civilizations, but the details didn't hold up well. Cometary emissions tend to be broad and diffuse, not sharply confined to a single frequency. The wow. Signal's narrow-band nature didn't fit comfortably with what we know about cometary radio emissions. Another possibility was terrestrial interference. Perhaps the signal came from Earth itself, from a satellite, an aircraft, or some ground-based transmitter. Radio interference is a constant problem in astronomy, and many false alarms have been traced back to human technology. However, the Big Ear telescope was specifically designed to filter out terrestrial signals, and the direction from which the "wow" signal appeared did not match any known satellite trajectories or aircraft paths at the time. No known Earth-based source could convincingly explain the signal's characteristics and timing. That left astronomers in an uncomfortable position. Every explanation had problems. The alien hypothesis was tantalizing but unsupported. Natural explanations were possible but unsatisfying. Terrestrial interference seemed unlikely, and because the signal never repeated, there was no way to gather new data to break the deadlock. The wow signal became a frozen moment in scientific history, a puzzle locked in place by its own uniqueness. This is why, decades later, it still matters. It represents a fundamental limitation in how we explore the universe. Astronomy is largely observational. We can't run experiments on stars or galaxies. We can only watch and measure. When something appears once and disappears forever, we're left with questions that may never have answers. And yet, the signal continues to play an important role, not because of what it proves, but because of what it reveals about our ignorance. It shows us that the universe is capable of producing phenomena that fall outside our expectations, events that don't fit neatly into our catalogs. It reminds us that silence in the data doesn't mean emptiness, and that a single unexplained signal can challenge decades of assumptions. Whether the wow signal was a strange natural event we don't yet understand, a rare coincidence, or something far more extraordinary, it stands as a symbol of cosmic uncertainty. Somewhere in the direction of the constellation Sagittarius, something emitted a powerful, precise radio signal for just over a minute, and then never did so again. We happen to be listening at exactly the right moment. That fact alone is humbling. It suggests that the universe may be full of fleeting events, signals, and phenomena that pass by unnoticed simply because we weren't looking at the right time or with the right tools. The wow signal doesn't give us answers. It gives us a reminder that our picture of the cosmos is incomplete, that our instruments catch only fragments of a much larger story, and that sometimes the most important discoveries are the ones that leave us with nothing but questions. If the wow signal taught astronomers how unsettling a single unexplained moment can be, the next mystery shows what happens when the universe refuses to stop misbehaving. Instead of a brief flash that vanishes forever, this one keeps repeating, over and over, daring scientists to explain it. It begins not with a radio telescope scanning the sky, but with a space telescope quietly watching the brightness of stars. In 2011, data from the Kepler Space Telescope revealed something profoundly strange about an otherwise unremarkable star. Its official catalog name is KIC 846-2852, but it became widely known as Tabby's star, named after the astronomer Tabitha Boyajian, who led the team investigating its behavior. At first glance, the star should have been boring. It sits about 1,460 light-years away, looks slightly larger and hotter than our Sun, and shows none of the obvious signs of instability that mark many variable stars. Yet the Kepler data told a very different story. Stars do dim from time to time, and astronomers are very familiar with this process. When a planet passes in front of its host star from our point of view, it blocks a small fraction of the star's light. This method, called the transit method, is one of the primary ways we detect exoplanets. The key word here is small. An Earth-sized planet blocks about 1/100% of a Sun-like star's light. Even Jupiter, the largest planet in our solar system, would only cause a dimming of about 1%. These dips are regular, predictable, and repeat with clockwork precision. Tabby's star did none of that. Instead, its brightness dropped erratically by enormous amounts. In some events, the star dimmed by 15%. In others, by more than 20%. That number alone should make you pause. To block 22% of a star's light, you need something vast, something comparable in scale to the star itself. No known planet, no matter how large, could produce such a dramatic effect. Even worse, the dimming events showed no consistent pattern. They didn't repeat on a fixed schedule. Some lasted days, others weeks. Sometimes the star dimmed slightly, sometimes catastrophically, and sometimes not at all for long stretches of time. From the perspective of planetary astronomy, this behavior made no sense. When the discovery was first announced, it triggered an explosion of speculation. Scientists and the public alike struggled to imagine what could cause such extreme and irregular dimming. One of the earliest ideas, and certainly the most famous, was that the star might be partially surrounded by an artificial structure. The concept traces back to physicist Freeman Dyson, who proposed in 1960 that an advanced civilization might build enormous structures to capture the energy output of its star. Not a solid shell, which would be physically implausible, but a swarm of orbiting collectors, now commonly referred to as a Dyson swarm. Such a structure would naturally block large, varying amounts of starlight as its components moved in complex orbits. The irregular, deep dimming seen in Tabby's star matched this idea uncomfortably well. To be clear, most astronomers never believed the alien megastructure explanation was likely. But the fact that it had to be discussed at all says something important. It wasn't proposed because scientists wanted aliens. It was proposed because conventional explanations were failing. When your data refuses to fit known categories, even extreme possibilities have to be acknowledged, if only to be ruled out later. Another hypothesis focused on comets. Perhaps the star was surrounded by a massive swarm of comets on elongated orbits. As these comets passed in front of the star, their dusty tails could block large amounts of light in an irregular fashion. This idea had the advantage of being natural and exotic at the same time. Comets are real, and we know they can produce dust clouds. But the numbers quickly became problematic. To block more than 20% of the star's light, you would need an enormous number of comets, far more than any known star system is expected to contain. And there was another issue. Dust from comets should leave a clear signature in infrared light, as it absorbs starlight and re-emits the energy as heat. Observations failed to find the expected infrared excess. The comet swarm explanation began to wobble. Dust clouds were the next candidate. Perhaps a large, uneven cloud of dust was orbiting the star, blocking light in unpredictable ways. This idea gained traction over time, especially as more observations accumulated. But dust alone raised questions. Where did it come from? Why was there so much of it? Why was it distributed in such a strange, uneven pattern? Some suggested the dust might be the aftermath of a massive collision, perhaps the destruction of a planet or moon. Such an event could produce a chaotic debris field capable of blocking starlight. Yet again, the lack of strong infrared emission complicated the picture. Stellar variability was also considered. Some stars naturally change brightness due to internal processes, but Tabby's star did not match any known class of variable stars. Its temperature, spectrum, and overall behavior placed it outside familiar categories. It was dimming too much, too irregularly, and without the accompanying changes that usually signal intrinsic stellar instability. As years passed, astronomers continued to monitor the star using ground-based telescopes and space observatories. Then came a crucial clue. In 2017, scientists observed one of the dimming events across multiple wavelengths of light. What they found was subtle but significant. The dimming was stronger in blue light than in red light. This is exactly what you would expect if small dust particles were blocking the star. Tiny dust grains scatter shorter wavelengths more efficiently than longer ones, the same reason Earth's sky appears blue. This wavelength-dependent dimming strongly favored dust as at least part of the explanation. It was a breakthrough, but not a complete solution. Dust could explain the color dependence, but it didn't fully explain the scale, structure, and persistence of the phenomenon. The star continued to dim in unpredictable ways, even after years of observation. No other star observed by Kepler or by any subsequent survey behaves quite like this. Out of hundreds of thousands of stars monitored with exquisite precision, Tabby's star remains unique. That rarity is perhaps the most unsettling aspect of all. If this were a common process, we would expect to see it elsewhere. We don't. Which means either the phenomenon is extraordinarily rare, or we are catching the star during an incredibly brief and unusual phase of its evolution. Neither option is especially comforting for neat theoretical models. Today, dust remains the leading explanation, but it is an incomplete one. It fits some observations and strains others. It explains the color dependence, but not the origin of the dust. It accounts for irregular dimming, but not its extreme depth. Tabby's star sits in an uncomfortable middle ground, partially understood but not explained. In this way, it mirrors the lesson of the wow signal. Some mysteries vanish as quickly as they appear, leaving only a single data point behind. Others linger, repeating just often enough to keep us guessing, but never enough to give up their secrets. Tabby's star reminds us that the universe doesn't just surprise us once and move on. Sometimes it keeps tapping us on the shoulder, again and again, quietly insisting that there is more going on than we currently understand. If Tabby's star unsettled astronomers by behaving like nothing else in its category, the next discovery pushed that discomfort onto a far larger stage. Instead of a single star acting strangely, this mystery appeared as vast structures imprinted across the fabric of the universe itself. Structures so large and so unexpected that, at first, many scientists assumed they had to be mistakes. In 2019, while astronomers were analyzing data from a new generation of radio telescopes, they stumbled upon shapes that simply did not belong. These objects were soon given a name that perfectly captured both their appearance and the scientific reaction to them. Odd radio circles, often shortened to ORCs. Unlike most astronomical discoveries, ORCs were not found by looking at visible light. If you point an optical telescope at their locations, you see almost nothing unusual. No glowing shells, no bright arcs, no dramatic explosions frozen in time. But when the same regions of sky are observed in radio wavelengths, enormous circular rings suddenly appear, faint but unmistakable, drawn across space like cosmic outlines. These circles are immense, spanning hundreds of thousands of light-years, and in some cases approaching or exceeding 1,000,000 light-years in diameter. To put that in perspective, the Milky Way itself is only about 100,000 light-years across. An ORC can be 10 times larger than our entire galaxy. The first of these objects was identified by astronomers working with the Australian Square Kilometre Array Pathfinder, commonly known as ASCAP. ASCAP was designed to rapidly survey large areas of the sky in radio frequencies with unprecedented sensitivity. Its wide field of view and advanced data processing capabilities allowed it to detect faint, diffuse radio structures that older telescopes would have missed entirely. When researchers began combing through ASCAP survey data, they noticed nearly perfect circles appearing in the radio maps. At first, the reaction was skepticism. Astronomy is full of artifacts, patterns introduced by data processing, calibration errors, or instrumental effects. Perfect circles are especially suspicious because nature rarely produces them so cleanly. The team assumed something had gone wrong in the analysis, but the circles persisted. Different data sets showed the same structures. Independent observations confirmed their existence. These were not glitches. They were real features in the radio sky. As more examples were found, astronomers began to catalog their shared properties. Every ORC detected so far appears only in radio wavelengths. They are invisible in optical, infrared, and X-ray observations, except for one intriguing detail. At the center of many ORCs lies an ordinary-looking galaxy, often an elliptical galaxy that appears completely unremarkable when observed in visible light. There are no obvious signs of extreme activity, no blazing jets, no violent collisions frozen in progress. Yet surrounding these quiet galaxies are enormous rings of radio emission, as if some vast event occurred long ago and left only a faint echo behind. The shapes themselves raise immediate questions. Astronomers are familiar with circular structures in space. Supernova remnants, for example, can form expanding shells of gas that look roughly circular. But supernova remnants are tiny compared to ORCs, typically spanning only a few dozen light-years. They also emit strongly in multiple wavelengths, not just radio. ORCs are far too large and too faint to fit this explanation. Planetary nebulae were also ruled out quickly. Despite the name, planetary nebulae have nothing to do with planets. They are shells of gas expelled by dying stars, and they can appear circular. But again, they are small, confined to our own galaxy, and easily visible in optical light. ORCs exist far beyond the Milky Way and dwarf planetary nebulae in scale. Another familiar phenomenon is radio galaxy lobes. Some galaxies host actively feeding supermassive black holes that launch powerful jets of particles at near light speed. These jets inflate enormous lobes of radio-emitting plasma that can stretch hundreds of thousands of light-years into space. From certain angles, these lobes can appear somewhat circular. But ORCs don't match this pattern either. The galaxies at their centers do not show the telltale signs of active black holes. There are no jets, no bright radio cores, no asymmetrical lobes. The rings are too clean, too symmetric, and disconnected from the usual machinery of radio galaxies. With conventional explanations exhausted, astronomers turned to more speculative ideas. One possibility is that ORCs are the remnants of colossal shock waves. Imagine a galaxy undergoing an intense episode of activity in its past, perhaps a burst of rapid star formation or a sudden awakening of its central black hole. Such an event could drive a powerful shock wave into the surrounding intergalactic medium. Over millions of years, that shock could expand outward, forming a vast spherical shell. As the shock interacts with tenuous gas, it could produce radio emission detectable today as a faint ring. This idea has some appeal. It explains the circular geometry and the association with a central galaxy. But it raises new questions. If this process is common, why are ORCs so rare? Galaxies experience active phases all the time, especially in the early universe. We should see far more of these structures if this were the dominant mechanism. Another hypothesis points to ancient energetic events, perhaps collisions or mergers that occurred billions of years ago. When galaxies merge, they release enormous amounts of energy into their surroundings. The interaction could generate expanding waves of magnetized plasma that persist long after the visible signs of the merger fade. ORCs could be the ghostly afterimages of such long-forgotten events, still glowing faintly in radio wavelengths. But once again, rarity becomes a problem. Galaxy mergers are common throughout cosmic history. ORCs are not. This mismatch suggests that if mergers are involved, only very specific and unusual conditions produce the observed rings. Some researchers have ventured even further into speculative territory, suggesting that ORCs might be linked to exotic physics from the early universe. In this view, the rings are not the result of individual galaxies at all, but rather the imprints of primordial processes, perhaps related to large-scale magnetic fields, topological defects, or other phenomena predicted by certain cosmological theories. These ideas are intriguing, but they remain highly theoretical. There is currently no direct evidence connecting ORCs to early universe physics, only the uncomfortable fact that nothing else seems to fit neatly. What makes ORCs particularly fascinating is not just that they are unexplained, but that they were hiding in plain sight. The radio sky has been studied for decades, yet these structures went unnoticed until recently. The reason is simple. Older radio telescopes either lacked the sensitivity to detect such faint, diffuse emission, or the wide field capability to recognize large-scale circular patterns. ASCAP changed that. It didn't just give astronomers better data, it gave them a new way of seeing. This is a recurring theme in modern astronomy. Every time we build a more capable instrument, we don't just answer old questions, we uncover entirely new ones. ORCs were not predicted by theory. No one was searching for them. They emerged organically from improved observations, reminding us that the universe often has surprises waiting just beyond the limits of our tools. As of now, only about a dozen ORCs have been identified, but that number is slowly growing as more surveys are conducted. Each new detection adds a piece to the puzzle, helping astronomers refine their ideas and rule out possibilities. Yet the core mystery remains intact. We know what ORCs look like. We know roughly how big they are. We know they are real. What we do not know is what creates them. In that sense, odd radio circles represent a new category of cosmic phenomenon, one that doesn't yet have a place in our mental map of the universe. They sit at the intersection of galaxies, intergalactic space, and deep cosmic time, whispering hints of events and processes we have yet to understand. Coming after the puzzles of the wow. Signal and Tabby's star, ORCs expand the scope of cosmic uncertainty even further. They show that mysteries are not confined to fleeting signals or peculiar stars. Sometimes the universe writes its questions on scales so large that they span millions of light years, visible only when we learn how to look in entirely new ways. Odd radio circles hinted that the universe could organize matter into vast, elegant shapes we never predicted. But the next discovery went even further, challenging not just specific models, but one of the deepest assumptions underlying modern cosmology itself. Instead of strange rings visible only in radio waves, astronomers began to notice enormous arrangements of galaxies, structures so large that, according to our best theories, they simply should not exist. These discoveries did not come from a single observation or a single telescope. They emerged gradually as large-scale galaxy surveys accumulated enough data to reveal patterns spanning billions of light years. In 2021, researchers analyzing the distribution of distant galaxies identified an immense structure now known as the Giant Arc. A few years later, in 2024, a second structure was announced in roughly the same region of the sky, dubbed the Big Ring. Together, they represent some of the largest coherent features ever observed in the universe. The Giant Arc is not a physical object in the traditional sense. It is not a wall or a filament you could point to in isolation. Instead, it is a vast, curved arrangement of galaxy clusters, stretching across approximately 3.3 billion light-years. That number is difficult to fully grasp. Light itself, traveling at the maximum speed allowed by physics, would take more than 3 billion years to cross from one end of the structure to the other. To put this in context, the entire observable universe is about 93 billion light-years across. The Giant Arc occupies a significant fraction of that scale. The Big Ring, while somewhat smaller, is still staggering in size. Measuring roughly 1.3 billion light-years in diameter, it appears as a nearly circular arrangement of galaxies, forming a ring-like pattern on the sky. Even more intriguing is the fact that both structures are located at roughly the same distance from Earth, around 9 billion light-years away, and appear in the same general region of the cosmos. This coincidence immediately raised eyebrows. When astronomers see one unusual structure, they consider the possibility of chance. When they see two, aligned in space and distance, the odds of coincidence begin to feel uncomfortably low. The reason these discoveries are so unsettling lies in a foundational idea known as the cosmological principle. This principle states that, on sufficiently large scales, the universe should look essentially the same in all directions. Matter may clump together locally, forming galaxies, clusters, and filaments. But when you zoom out far enough, those irregularities should average out. The universe should be homogeneous, meaning roughly uniform in composition, and isotropic, meaning it looks the same no matter which way you look. This assumption is not philosophical. It is built directly into the mathematical framework of modern cosmology. It underpins the standard model of the universe and is strongly supported by observations of the cosmic microwave background, which shows that the early universe was extraordinarily uniform, with only tiny fluctuations in density. From these small fluctuations, gravity gradually built the large-scale structure we see today. However, this process has limits. Based on how fast information can travel and how long the universe has existed, there is a maximum size that coherent structures should be able to reach. Calculations suggest that structures larger than about 1 to 1.2 billion light-years should be extremely unlikely, if not impossible. Beyond that scale, the universe should smooth out. The Giant Arc and the Big Ring blow past this limit. The Giant Arc, in particular, is nearly 3 times larger than what standard theory allows. This immediately raises a difficult question. Are these structures real, or are we being misled by patterns in noisy data? Astronomers are acutely aware of the human tendency to see shapes where none exist. When you plot the positions of millions of galaxies, random alignments can sometimes look meaningful. A curved arrangement might emerge purely by chance, especially if you're looking for one. This skepticism is healthy, and it was the first response from many researchers. To address this, the teams studying these structures performed careful statistical analyses. They asked a simple question: if galaxies were distributed randomly according to known cosmic statistics, how likely would it be to see a structure like this? For the Giant Arc, the probability of it being a random alignment was estimated at roughly 1 in several thousand. That does not make it impossible, but it does make it unlikely. The Big Ring showed similar statistical significance. More importantly, the fact that both structures appear in the same region of space strengthens the case that something real is being observed. Two unlikely coincidences occurring together are harder to dismiss than one. Assuming these structures are real, the next step is explanation. One possibility involves baryon acoustic oscillations, often abbreviated as BAO. In the early universe, before atoms formed, matter and radiation were tightly coupled in a hot plasma. Sound waves rippled through this plasma, creating regions of slightly higher and lower density. When the universe cooled enough for atoms to form, these sound waves froze in place, leaving a preferred scale in the distribution of matter. Billions of years later, this scale can still be detected as a subtle pattern in how galaxies are arranged. BAO provides a kind of cosmic ruler, and it is an essential tool for measuring the expansion of the universe. Could the giant arc or the Big Ring be exaggerated manifestations of this process? At first glance, the idea seems appealing, especially for the Big Ring, which has a roughly circular shape. But the numbers don't cooperate. The characteristic scale of baryon acoustic oscillations is about 500 million light-years. Both the giant arc and the Big Ring are far larger than this, by factors of 2 to 6. They do not match the expected size or statistical behavior of BAO features. That explanation, while elegant, falls short. Another idea draws from more speculative physics: cosmic strings. These are hypothetical one-dimensional defects in spacetime that may have formed during phase transitions in the early universe. If they exist, cosmic strings would be incredibly thin but immensely dense, stretching across vast distances. As matter fell into the gravitational influence of a cosmic string, galaxies could form along its length, potentially creating large, coherent structures. Cosmic strings could, in principle, generate features larger than standard structure formation models allow. The problem is that cosmic strings remain purely theoretical. Despite decades of searching, there is no direct observational evidence that they exist. Invoking them to explain the giant arc and Big Ring feels premature, though not impossible. It places these structures at the edge of what we can currently test. A third possibility is that our cosmological models are incomplete. This is perhaps the most uncomfortable option, but also the most profound. If structures larger than the theoretical limit truly exist, then one or more of our assumptions may need revision. The cosmological principle might not hold as strictly as we thought. The universe might be more clumpy and anisotropic on the largest scales than our models predict. This would not mean that the Big Bang theory is wrong, or that everything we know about cosmology collapses. It would mean that the details of how structure grows, especially over billions of years, are more complex than our simplified descriptions capture. Historically, this would not be unprecedented. Many times in science, principles once thought universal turned out to be approximations. Newton's laws work beautifully at everyday speeds, but fail near the speed of light. Classical physics describes the macroscopic world, but breaks down at quantum scales. The cosmological principle itself is an assumption, albeit a well-supported one. Discoveries like the giant arc and Big Ring force us to ask whether that assumption has limits we are only now beginning to see. At present, the debate is far from settled. Some astronomers remain unconvinced that these structures are truly physical entities. Others argue that the statistical evidence is strong enough to take them seriously. New surveys and independent analyses will be crucial. If similar structures are found elsewhere, the case for a real challenge to standard cosmology will grow stronger. If not, these may remain rare anomalies, intriguing but ultimately reconcilable with existing theory. Either way, their impact is already significant. Like odd radio circles, The giant arc and big ring were not predicted. They emerged from data that became available only because our instruments and surveys reached new levels of scale and precision. They remind us that the universe does not arrange itself for our convenience. Sometimes, it presents patterns that fit beautifully within our theories. Other times, it stretches those theories to their breaking point. These immense structures stand as potential cracks in our current understanding, not yet wide enough to cause collapse, but impossible to ignore. They suggest that the story of cosmic structure formation may still have chapters we have not read, written across distances so vast that only now are we beginning to see them. If the giant arc and the big ring challenge us by being too full, too structured, and too large, the next mystery confronts us from the opposite direction. It is not a place where matter gathered in excess, but a region where matter seems to be missing almost entirely. In the vast architecture of the universe, this absence is just as unsettling as any colossal structure. This region is known as the Botha's Void, and it represents one of the most extreme examples of cosmic emptiness ever discovered. Located roughly 700 million light-years from Earth and spanning about 330 million light-years across, the Botha's Void is enormous. To grasp its scale, consider that the Milky Way is about 100,000 light-years in diameter. You could place more than 3,000 Milky Ways side by side across the width of this void. Based on the average density of galaxies in the universe, a volume of space this large should contain thousands of galaxies. Instead, astronomers find only a few dozen. The rest is almost completely empty. The Botha's Void was identified in the early 1980s when astronomers were mapping the large-scale distribution of galaxies. As survey data accumulated, a striking pattern emerged. Galaxies were not spread evenly throughout space. Instead, they traced out filaments, walls, and clusters, forming what is now known as the cosmic web. Between these dense regions lay vast empty areas called voids. Voids themselves are not unusual. They are a natural outcome of gravitational evolution. But the Botha's Void stood out immediately. It was far larger and emptier than typical voids, pushing the limits of what theoretical models predicted. To understand why this matters, it helps to look at how structure forms in the universe. Shortly after the Big Bang, the universe was hot, dense, and remarkably uniform. Tiny fluctuations in density existed, seeded by quantum effects during a period of rapid expansion known as inflation. These fluctuations were minuscule, differences of only 1 part in 100,000. But gravity amplified them over billions of years. Regions that were slightly denser than average attracted more matter, growing into galaxies and clusters. Regions that were slightly less dense lost matter to their surroundings, becoming voids. Over time, this process produced the cosmic web, with matter flowing away from underdense regions and piling up along filaments and nodes. Computer simulations of this process do an impressive job of reproducing the large-scale structure we observe today. They naturally generate voids surrounded by walls and filaments of galaxies. However, these simulations also predict limits. There is only so much matter that can flow out of a region over the age of the universe. As a result, voids should not grow arbitrarily large or empty. The Botha's Void sits uncomfortably close to those limits. It is not strictly impossible according to theory, but it is an extreme case, the tail end of the statistical distribution. That alone makes it scientifically valuable. Extreme examples often reveal where models are weakest or incomplete. What makes the Botha's Void even more intriguing is not just its size, but the nature of the galaxies found within it. The few galaxies that do exist inside the void are strange. Many of them show signs of unusually high star formation rates, despite their isolation. Others have irregular shapes or chemical compositions that differ from galaxies in denser environments. This is unexpected. In crowded regions of the universe, galaxies are constantly interacting. They tug on each other gravitationally, collide, merge, and strip gas from one another. These interactions strongly influence how galaxies evolve. In the Bode's void, those interactions are almost entirely absent. A galaxy inside the void may have no close neighbors for tens of millions of light years. It evolves in near-complete isolation. This isolation turns the Bode's void into a kind of natural laboratory. By studying galaxies inside it, astronomers can explore how galaxies evolve when external influences are minimized. Some theories suggest that isolated galaxies should retain more of their original gas, allowing them to form stars for longer periods. Others predict slower evolution and simpler structures. The observations from the Bode's void provide mixed signals, suggesting that galaxy evolution is more nuanced than simple models imply. Some void galaxies appear to be forming stars efficiently, while others look oddly underdeveloped, as if their growth stalled early on. These differences hint that environment plays a powerful but complex role in shaping galaxies. The existence of the Bode's void also ties back to the earliest moments of the universe. If voids form from initial underdensities, then the Bode's void must have originated from a region that was unusually empty even in the very early universe. That raises deeper questions. Why did this particular region start out with such a low density? Inflation predicts random fluctuations, so extreme regions are possible, but rare. The Bode's void may be the result of one such rare fluctuation, a cosmic accident amplified over billions of years. A microscopic difference in density shortly after the Big Bang could have grown into a void hundreds of millions of light years across. This idea is both elegant and unsettling. It suggests that some of the largest features in the universe trace their origins back to quantum randomness in the first fraction of a second after time began. In this sense, the Bode's void is a bridge between the smallest and largest scales in physics, connecting quantum fluctuations to the cosmic web. There are also broader implications. If voids like Bode's exist, they can affect how we interpret other observations. Light traveling through a void experiences different gravitational conditions than light passing through dense regions. This can subtly influence measurements of cosmic expansion and the distribution of matter. Some researchers have even explored whether large voids could contribute to anomalies seen elsewhere, such as unusual temperature patterns in the cosmic microwave background. While the Bode's void alone cannot explain such effects, it highlights how inhomogeneities in the universe can complicate our measurements and interpretations. Like the giant arc and Big Ring, the Bode's void challenges the idea that the universe smooths out neatly on large scales. It does not overthrow the cosmological principle, but it stretches it. The universe may be statistically uniform when averaged over enormous volumes, yet still contain extreme regions that defy our intuition. These extremes matter because they test the robustness of our theories. If our models can account for both the densest structures and the emptiest voids, then they are likely on the right track. If not, revisions may be needed. The Bode's void also reinforces a recurring theme in modern cosmology. Many of the most interesting discoveries are not objects in the traditional sense, but patterns, absences, and distributions. A void is defined not by what it contains, but by what it lacks. Yet that lack carries information. It tells us about the flow of matter, the growth of structure, and the initial conditions of the universe. In this way, emptiness becomes just as informative as abundance. Seen alongside the immense structures discussed earlier, the Buddha's void completes a kind of cosmic contrast. On one end of the spectrum, we find structures so large they threaten theoretical limits. On the other, regions so empty they test how far matter can evacuate space. Both extremes arise from the same underlying physics: gravity acting on tiny initial fluctuations over immense spans of time. Together, they suggest that the universe is capable of producing far more dramatic variations than our simplified pictures often convey. The Buddha's void stands as a reminder that cosmic evolution is not just about building things up, but also about carving things out. Matter does not merely gather, it flows, evacuates, and leaves behind vast expanses of near-nothingness. By studying these empty regions, astronomers gain insight into the forces that shaped everything else. In that sense, the void is not an absence of meaning, but a concentrated source of it, a silent region that speaks volumes about how the universe came to be and how it continues to evolve. If the Buddha's void teaches us how emptiness can stretch our theories of structure formation, the next mystery pushes that tension all the way back to the earliest light the universe ever produced. Unlike voids, galaxies, or enormous arcs of matter, this anomaly is not something that formed over billions of years. It is a feature imprinted on the universe when it was still young, long before the first stars or galaxies existed. To understand why it is so troubling, we first need to understand what it is imprinted on: the cosmic microwave background, often shortened to the CMB. The CMB is the oldest light we can observe. It dates back to a time about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before this moment, the universe was opaque. Light could not travel freely because it was constantly scattering off charged particles. Once neutral atoms formed, photons were suddenly free to move through space. Those photons have been traveling ever since, stretched by cosmic expansion into microwave wavelengths. Today, we observe them as a faint glow coming from every direction in the sky, remarkably uniform, with a temperature of about 2.7 degrees above absolute zero. That uniformity is one of the strongest pieces of evidence for the Big Bang model. Wherever we look, we see nearly the same temperature. But nearly is doing important work here. Embedded within that smooth background are tiny fluctuations, temperature differences at the level of 1 part in 100,000. These variations are not noise. They are the fingerprints of the universe's earliest density fluctuations. Slightly denser regions appear slightly cooler, and those regions would later grow into galaxies and clusters under the influence of gravity. By mapping these fluctuations, cosmologists can reconstruct the initial conditions of the universe with extraordinary precision. Satellites like COBE, WMEP, and Planck have measured the CMB in exquisite detail, turning it into one of the most powerful tools in modern cosmology. And it was in these detailed maps that something unexpected appeared. In the early 2000s, researchers noticed a region of the sky that stood out starkly from the rest. This area was significantly colder than surrounding regions, far colder than standard models predicted. It became known as the CMB cold spot. The cold spot spans roughly 10 degrees across the sky, an enormous angular size, about 50 times the apparent diameter of the full moon. Its shape is roughly oval, and its temperature is about 70 microkelvin colder than the average CMB temperature. That may sound minuscule, but in the context of the CMB's incredibly small fluctuations, it is enormous. What makes the cold spot unsettling is not just its existence, but its improbability. Based on the standard cosmological model, scientists can calculate how likely it is for random fluctuations to produce a region this large and this cold. The answer is about 2%. That does not make it impossible. Rare things happen, but it does make it uncomfortable. If you were to generate 100 universes with random initial conditions following the same physical laws, only about 2 of them would be expected to contain a feature like this. We live in one universe, and we appear to be in one of those rare cases. The question is whether that rarity is meaningful or just bad luck. The first line of investigation was to ask whether something along the line of sight could be responsible. Light traveling through the universe does not move through a static landscape. It passes through regions of varying density, climbing in and out of gravitational wells. This process can subtly change the energy of photons, an effect known as the integrated Sachs-Wolf effect. If a photon passes through a large underdense region, a supervoid, it can lose a small amount of energy, appearing slightly cooler when it reaches us. Given what we learned from the Buddha's void, this idea was particularly appealing. Perhaps the cold spot was caused by an enormous void between us and the surface of last scattering. Astronomers searched for such a void and did find evidence of a relatively large underdense region in that direction. However, when they ran the numbers, the explanation fell short. The void that exists is not large or empty enough to account for the full temperature drop observed in the cold spot. At best, it could explain a fraction of the anomaly. To fully reproduce the cold spot through this mechanism, the universe would need to contain a void even larger and emptier than any we have observed. That pushed the explanation beyond what current data supports. Another possibility is that the cold spot is simply a statistical fluke. With only one universe to observe, unlikely events are unavoidable. Someone, somewhere, always wins the cosmic lottery. Perhaps we just happen to live in a universe where a rare fluctuation occurred. This explanation has the advantage of requiring no new physics. It is conservative, cautious, and deeply unsatisfying. Scientists tend to accept statistical explanations only after all other avenues have been exhausted, because they offer no deeper insight. They explain the anomaly by effectively saying it means nothing. Yet with only one universe to work with, this possibility cannot be ruled out. We cannot rerun the cosmos and see how often the cold spot appears. We are stuck with a single realization of the cosmic experiment. Then there is the most speculative explanation of all. Some theories of cosmic inflation suggest that our universe may be just one bubble in a vast multiverse, a landscape of many universes with varying properties. In this framework, it is possible for bubble universes to collide during their formation. Such a collision could leave a circular imprint on the CMB, a region slightly hotter or colder than its surroundings. The cold spot has roughly the right size and shape to fit this idea. If true, it would be extraordinary, evidence of physics beyond our universe itself. But extraordinary claims demand extraordinary evidence, and here the evidence is thin. There is no independent confirmation of a multiverse, and no clear prediction that uniquely ties the cold spot to such a collision. This explanation remains firmly in the realm of speculation. What makes the cold spot especially challenging is that it exposes the limits of cosmological inference. In most areas of science, repeated experiments allow probabilities to be tested directly. In cosmology, we do not have that luxury. We cannot observe multiple universes. We cannot reset initial conditions. We infer laws from a single cosmic history. This makes it extremely difficult to decide whether an anomaly is a profound clue or a meaningless outlier. The cold spot sits precisely at this boundary. It is unusual enough to raise eyebrows, but not so extreme that it forces an immediate revision of theory. As a result, it has lingered for more than 2 decades without resolution. In a way, the cold spot mirrors the Botha's void on a different level of cosmic history. The void represents an extreme outcome of structure formation over billions of years. The cold spot represents a potential anomaly baked into the universe almost from the beginning. One challenges our understanding of how matter moves and clusters. The other challenges our understanding of the initial conditions themselves. Together, they suggest that cosmic history may contain rare but significant deviations from the statistical norms we rely on. The cold spot also underscores a broader theme that runs through all these mysteries. Our models of the universe are incredibly successful. They explain an astonishing range of observations with remarkable precision, but they are still models. They are built on assumptions, averages, and probabilities. Anomalies like the cold spot do not necessarily overthrow those models, but they remind us that reality is messier than our equations. Sometimes, the universe produces features that sit at the edges of what we expect, features that force us to confront the limitations of our knowledge. Whether the cold spot is a supervoid's shadow, a rare statistical accident, or the faint scar of an encounter with another universe, it serves as a powerful reminder. We are trying to understand the universe from the inside, with only one example to study. That makes certainty elusive. The cold spot remains a question mark stamped onto the oldest light in existence, a silent reminder that even our clearest picture of the early cosmos may still be incomplete. After the cold spot forces us to confront how little we can infer from a universe we can only observe once, the next mystery brings that same uncertainty much closer to home. It is not written across billions of light years or frozen into the oldest light in existence. Instead, it appears in the atmosphere of a single star, quietly violating the rules of nuclear physics in a way that has refused to go away for decades. This anomaly does not ask whether our cosmological models are incomplete. It asks whether our understanding of how stars themselves work might still be missing something fundamental. The star in question is commonly known as Przybylski's star, named after the astronomer Antoni Przybylski, who studied it in the 1960s. On the surface, it looks like a relatively ordinary star, slightly hotter than the Sun, and well into the later stages of its life. But when astronomers analyzed its spectrum, the fingerprint of elements present in its atmosphere, they found something deeply unsettling. The star appeared to contain significant amounts of radioactive elements that should not be there at all. Among these were technetium and promethium, 2 elements with no stable isotopes. Technetium's longest-lived isotope has a half-life of only a few million years. Promethium's isotopes decay even faster. In cosmic terms, these are fleeting moments. Stars like Przybylski's are billions of years old. Any technetium or promethium that was present when the star formed should have decayed into other elements long ago. And yet, there they were, clearly visible in the star's spectrum. This was not a subtle effect. The spectral lines were strong, unambiguous, and persistent. Astronomers checked and rechecked the data. The measurements held up. The problem was not that the elements were misidentified. The problem was that they existed at all. To appreciate why this is so disturbing, it helps to understand how elements are normally created in stars. Most elements heavier than hydrogen and helium are forged through nuclear fusion and neutron capture processes inside stars. In certain stages of stellar evolution, stars can produce unstable elements, but these are typically short-lived and only appear under specific conditions. In some evolved stars, for example, Technetium can be produced through the slow neutron capture process and brought to the surface through convective mixing. This is known as dredge-up. When technetium is observed in such stars, it makes sense because the star is actively creating it. Przybylski's star does not fit this picture. It is not in a phase of evolution where these processes should be operating. It lacks the internal conditions required to continuously generate short-lived radioactive elements. That immediately ruled out the simplest explanation. Perhaps then, some unknown nuclear process was at work. This was one of the earliest ideas proposed. Maybe there are nuclear reactions occurring in certain stars that we do not yet understand, reactions capable of producing technetium, promethium, and even heavier elements near the star's surface. The problem with this idea is that nuclear physics is extremely well tested. The reactions that occur in stars are constrained by fundamental forces that have been studied in laboratories and in countless astrophysical environments. Introducing a new nuclear process powerful enough to produce these elements without disrupting everything else would require physics far beyond anything currently supported by evidence. Over the years, no such mechanism has been identified. Another idea returned to convective dredge-up, but in a more exotic form. Perhaps Przybylski's star experienced an unusual mixing event in the past, bringing freshly synthesized radioactive material from its interior to its surface. This would require the star to have gone through an evolutionary phase that standard stellar models do not predict for stars of its type. Simulations have been run, parameters tweaked, and edge cases explored. None of them reproduce the observed abundances. Worse still, the elements are not just present. They are present in extreme quantities. Przybylski's star shows overabundances of many rare elements, including lanthanides and other heavy species, far beyond what is seen in similar stars. The pattern is not random. It is structured, systematic, and stubbornly resistant to explanation. This led to one of the more imaginative proposals: the involvement of superheavy elements. Nuclear physicists have long predicted the existence of an island of stability, a region of the periodic table where superheavy elements might have relatively long half-lives compared to their neighbors. If such elements exist, they could decay into technetium, promethium, and other radioactive species over extended periods of time. In this scenario, Przybylski's star might contain traces of these super-heavy elements, slowly decaying and replenishing the short-lived isotopes we observe. It is an intriguing idea because it links stellar anomalies to unresolved questions in nuclear physics, but it remains speculative. No super-heavy elements from the island of stability have ever been directly observed, either in laboratories or in astrophysical environments. Invoking them to explain the star replaces one mystery with another. Even if such elements exist, it is unclear how they would become concentrated in the atmosphere of a single star in such extraordinary amounts. Decade after decade, astronomers have returned to Przybylski's star with better instruments and more refined techniques. High-resolution spectroscopy has confirmed the presence of radioactive elements again and again. Improved models of stellar atmospheres have not made the problem go away. If anything, they have sharpened it. The anomaly has persisted through generations of technology, surviving every attempt to explain it away as an artifact or misunderstanding. That persistence is what elevates this star from a curiosity to a genuine challenge. It is easy to dismiss a single odd measurement. It is much harder to dismiss a phenomenon that continues to appear no matter how carefully you look. There is also an unsettling implication hidden in this mystery. If Przybylski's star truly contains ongoing sources of radioactive elements, it suggests that stellar atmospheres may be far more dynamic and chemically complex than we currently believe. The clean separation between nuclear processes deep inside stars and the calm, passive outer layers may be an oversimplification. Alternatively, it may suggest that rare, poorly understood processes can dominate under specific conditions, producing outcomes that defy our general rules. Either possibility points to gaps in our knowledge. Like the cold spot, this anomaly highlights a fundamental limitation. We build our theories by studying many examples and identifying patterns. Most stars behave as expected. Most stellar spectra make sense. But a single object that refuses to conform can expose hidden assumptions. Przybylski's star does exactly that. It asks whether our understanding of stellar evolution is complete, or whether there are rare pathways that we have barely begun to imagine. It also reminds us that time itself plays a crucial role in astronomy. Radioactive elements act as cosmic clocks. Their presence or absence tells us how long processes have been operating. When those clocks appear to be broken, it undermines one of our most powerful tools for understanding cosmic history. For more than half a century, Przybylski's star has remained an unsolved puzzle. It does not announce itself with dramatic explosions or vast cosmic structures. It simply sits there, quietly displaying spectral lines that should not exist. That quiet persistence is what makes it so unsettling. In a universe already filled with enormous voids, improbable patterns, and ancient anomalies, this star adds a different kind of mystery. It suggests that even the well-studied physics of stars may still hold surprises, and that some of the most profound questions are not written across the sky, but hidden in the fine details of light itself. After a single star quietly defying nuclear physics for decades, the next mystery arrives not as a distant anomaly, but as a visitor that passed directly through our own cosmic neighborhood. It did not announce itself with radiation or explosions. It appeared as a faint point of light, moving too fast, on a trajectory that immediately told astronomers something unprecedented was happening. For the first time in human history, we were watching an object from another star system pass through the solar system. In October 2017, astronomers using the Pan-STARRS Survey Telescope in Hawaii detected an unusual object moving rapidly against the background stars. It was given the designation Oumuamua, a Hawaiian word meaning scout or messenger from afar, a fitting name for something that had traveled across interstellar space long before Earth ever existed. From the very beginning, Oumuamua refused to behave like anything astronomers had seen before. Its trajectory was the first clue. Unlike asteroids or comets bound to the sun, Oumuamua was on a hyperbolic path. It came from outside the solar system, passed close to the sun, and then left, never to return. This alone made it historic. But as observations continued, the strangeness only deepened. Based on how its brightness changed as it rotated, astronomers inferred that Oumuamua had an extreme shape. Early estimates suggested it might be 10 times longer than it was wide, far more elongated than typical asteroids. Later models proposed it could be disc-like instead, thin and flattened rather than cigar-shaped. Either way, it was unlike the rubble pile asteroids we are familiar with. No object in our solar system has such an extreme geometry. Then there was the issue of what Oumuamua did not have. As it passed close to the sun, it should have behaved like a comet. Comets heat up, releasing gas and dust that form a visible coma and tail. Oumuamua showed no such features. Even the most sensitive telescopes failed to detect any surrounding cloud of dust or gas. This absence was puzzling, because another anomaly soon emerged that strongly suggested outgassing of some kind was occurring. Precise tracking of Oumuamua's motion revealed that it was accelerating slightly as it moved away from the Sun. Gravity alone could not account for this extra push. Something was providing additional force. In comets, that force comes from jets of gas released as ice sublimates. But if Oumuamua was outgassing, it was doing so invisibly. This combination of non-gravitational acceleration and lack of a visible coma was unprecedented. Astronomers were forced into a corner. Either our understanding of cometary behavior was incomplete, or Oumuamua was something fundamentally different. One proposed solution was that Oumuamua was releasing gas, but not the kind we usually see. Instead of water vapor, it might have been outgassing hydrogen, nitrogen, or even hydrogen ice itself. Hydrogen gas is difficult to detect, especially at interstellar distances, and could in principle produce acceleration without a visible tail. Another idea suggested nitrogen ice, similar to the surface of Pluto, sublimating under solar heating. These explanations had the advantage of being natural and exotic at the same time. They did not require new physics, only unfamiliar compositions. But they raised new questions. How common are such objects? How do they form in other star systems? And why have we never seen anything like this in our own solar system? Radiation pressure offered another possibility. Sunlight carries momentum, and when it reflects off an object, it exerts a small force. For most objects, this effect is negligible. But if Oumuamua were extremely thin and lightweight, radiation pressure could account for the observed acceleration. This idea fit the data surprisingly well. The problem was the implied structure. To be pushed significantly by sunlight, Oumuamua would need to be unusually thin, with a very high surface area to mass ratio. Natural objects rarely form this way. At this point, the conversation took a controversial turn. A small number of researchers suggested that Oumuamua might be artificial, perhaps a light sail built by an extraterrestrial civilization. A light sail is a thin, reflective structure designed to be propelled by radiation pressure. The observed acceleration matched what such a sail might experience. Combined with Oumuamua's strange shape and lack of outgassing, the idea gained public attention almost immediately. It is important to be precise here. The proposal was not that Oumuamua was definitively alien technology. It was that, based on the data available, an artificial origin could not be completely ruled out. In science, ruling out possibilities matters as much as confirming them. Still, the hypothesis was deeply controversial. Most astronomers strongly favored natural explanations, arguing that invoking alien technology was unnecessary and premature. The debate itself became part of the story, highlighting the tension between conservative interpretation and openness to the unexpected. As more studies were published, no explanation emerged as fully satisfying. Every model explained some aspects of Oumuamua's behavior and struggled with others. Hydrogen outgassing could explain acceleration, but raised formation problems. Nitrogen ice required specific and rare conditions. Radiation pressure worked dynamically, but implied an unusual structure. The artificial hypothesis fit the acceleration, but lacked any independent supporting evidence. The most frustrating aspect of all was that Oumuamua was already gone. By the time astronomers realized how strange it truly was, it was receding rapidly, too faint to study in detail. There was no opportunity to send a probe, no chance for follow-up observations. The window had closed. Like the wow signal decades earlier, Oumuamua left us with a single, fleeting data set. One object, one pass, no repetition. That limitation looms over every discussion of its nature. With only one example, it is impossible to know whether Oumuamua is representative of a common class of interstellar objects or a rare outlier. Future detections may resolve the mystery. New surveys are expected to discover many more interstellar visitors in the coming years. If those objects behave similarly, Oumuamua may become understandable in hindsight. If they behave differently, it may remain unique. In either case, Oumuamua has already changed astronomy. It forced scientists to confront the reality that interstellar space is not empty, that objects from other star systems regularly pass through our own, unseen until recently. It exposed gaps in our models of small-body physics and planetary system formation, and it reminded us how much depends on timing. The universe does not wait for us to be ready. Sometimes it sends a messenger through our solar system once, briefly, and then it is gone forever. Like Przybylski's star, Oumuamua persists as an unresolved anomaly, not because it is loud or dramatic, but because it does not fit. It sits at the intersection of planetary science, astrophysics, and the search for life, refusing to settle into any category. Whether it was an exotic natural fragment shaped by alien stars or something even more extraordinary remains unknown. What is certain is that for a brief moment, something truly foreign passed through our cosmic backyard, and we are still trying to understand what we saw before it vanished into the dark. After Oumuamua reminded us how easily a single fleeting event can escape full understanding, the next mystery escalates that frustration to a cosmic scale. Instead of a small object slipping through unnoticed until it was already gone, this phenomenon announced itself with an explosion so bright it briefly outshone entire galaxies. And yet, despite its intensity, it vanished almost as quickly as it appeared, leaving astronomers scrambling to explain what they had just witnessed. These events are now known as fast blue optical transients, or FBOTs, and they represent one of the most puzzling new classes of cosmic phenomena discovered in the modern era. The story begins in June 2018, when automated sky surveys detected an extremely bright flash of light in a distant galaxy about 200 million light-years away. The object was officially catalogued as AT2018 Cow, but astronomers quickly gave it a more memorable nickname, the Cow, derived from the last letters of its designation. At first glance, it looked like a supernova, the explosive death of a massive star. Supernovae are among the brightest events in the universe, capable of briefly rivaling the combined light of billions of stars. But within days, it became clear that this was no ordinary supernova. AT2018 Cow rose to peak brightness astonishingly fast, reaching its maximum luminosity in just a few days. Typical supernovae take weeks to brighten. Then, just as rapidly, it began to fade. The entire event unfolded on a timescale far shorter than any known stellar explosion. The color of the light added another layer of strangeness. AT2018 Cow was unusually blue, indicating extremely high temperatures. Supernovae often start hot and then cool as their expanding debris radiates energy away. The Cow remained hot far longer than expected, suggesting a persistent energy source at its core. Even more puzzling, observations across multiple wavelengths revealed that the explosion was remarkably compact. Radio and X-ray emissions indicated that something dense and energetic was still present at the center long after the initial flash. In standard supernova models, the explosion blasts material outward, and the core is quickly hidden behind an expanding shell of debris. In AT2018 Cow, the core seemed exposed, as if the explosion had failed to fully shroud whatever was powering it. As astronomers gathered more data, the list of inconsistencies grew. The spectral features did not match known supernova types. There was evidence of high-velocity material, but not in the patterns expected from stellar collapse. The brightness was too high, the rise too fast, the evolution too strange. It became increasingly clear that AT 2018 Cow did not belong to any established category. And then, as researchers searched archival data and monitored the sky more carefully, they found more events like it. Not many, but enough to establish a pattern. These fast, luminous blue transients were real, and AT 2018 Cow was simply the first well-studied example. With a new class of phenomena emerging, theorists rushed to explain what could produce such behavior. One leading idea involves the birth of a compact object, either a neutron star or a black hole, formed in a failed or unusual stellar collapse. In this scenario, a massive star begins to explode, but instead of producing a typical supernova, the core collapses into a compact object that continues to inject energy into the surrounding material. A rapidly spinning neutron star, known as a magnetar, could provide such power. Magnetars possess extraordinarily strong magnetic fields and can release enormous amounts of energy as they spin down. This ongoing energy injection could keep the explosion hot and bright, while also explaining the fast rise and unusual emission. The challenge with this explanation is that it requires finely tuned conditions. The explosion must eject just enough material to produce a bright optical signal, but not so much that it smothers the central engine. While possible, it is not clear how often nature produces such precise outcomes. Another idea involves exotic tidal disruption events. Normally, tidal disruptions occur when a star wanders too close to a supermassive black hole at the center of a galaxy. The star is torn apart by tidal forces, producing a bright flare that can last months or even years. AT 2018 Cow-like events are far too fast for this classic scenario. However, if a smaller black hole or neutron star were involved, or if the disrupted object were unusually compact, the timescale could be shorter. Some models propose that a star or dense stellar remnant was shredded by an intermediate mass black hole, producing a brief but intense burst of radiation. This explanation can reproduce some aspects of the observed light curves, but it struggles to account for others, particularly the early optical brightness combined with later high-energy emission. Compact object collisions have also been proposed. The merger of two neutron stars, or a neutron star and a black hole, is known to produce powerful explosions and gravitational waves. These events can generate short gamma-ray bursts and kilonovae. However, the known signatures of such mergers do not align well with FBOTs. The timescales, colors, and energy distributions differ significantly. While some hybrid or off-axis versions of these collisions have been explored, none provide a fully satisfying match to the data. As with many of the anomalies discussed so far, every explanation fits part of the picture and fails elsewhere. What makes FBOTs particularly challenging is how quickly they evolve. Astronomers often rely on long observation campaigns to disentangle complex physical processes. FBOTs do not grant that luxury. They appear suddenly, peak within days, and fade rapidly. If telescopes are not pointed in the right direction at the right time, crucial information is lost. AT 2018 Cow was studied intensely only because it was relatively nearby and bright. Most FBOTs are discovered farther away and observed less completely. This observational bias adds another layer of uncertainty. Despite these challenges, the growing evidence points to one unavoidable conclusion. Fast blue optical transients are not just odd supernovas or rare outliers. They represent a genuinely new category of cosmic event. Their properties cluster together in ways that distinguish them from known explosions. Their existence suggests that the universe has additional ways of releasing energy, pathways that sit between familiar stellar deaths and more exotic high-energy phenomena. In that sense, FBOTs echo many of the earlier mysteries, like the WOW signal. They appear suddenly and leave limited data behind. Like Tabby's star and Przybylski's star, they resist classification within established frameworks. Like Oumuamua, they highlight how timing and chance shape what we can learn. We are only beginning to detect these events because modern surveys scan the sky continuously with high cadence and sensitivity. A generation ago, AT2018 COW would likely have gone unnoticed, its brief flash lost in the gaps between observations. As more FBOTs are discovered, patterns may emerge that clarify their origins, or they may diversify, revealing multiple underlying mechanisms. Either outcome would reshape our understanding of stellar death and high-energy astrophysics. For now, AT2018 COW stands as the prototype of something new, a cosmic explosion that burns hot and fast, then fades, leaving behind more questions than answers. It reminds us that even the most violent events in the universe can be fleeting, and that the cosmos still has surprises capable of overwhelming our carefully constructed categories. After explosions that burn too fast and too bright, the next mystery slows everything down and forces us to confront time itself. Not time as we experience it, but cosmic time, the clock that measures the age of the universe. Up to now, many of these anomalies have challenged how things form, evolve, or disappear. This one challenges something even more basic: whether we truly know how old things are. At the center of this puzzle is a single ancient star whose estimated age appears to brush uncomfortably close to the age of the universe itself. This object is often called the Methuselah star, formally catalogued as HD 1.0283. It lies relatively nearby, about 190 light-years from Earth, in the halo of our galaxy. Unlike the exotic explosions or fleeting visitors discussed earlier, this star has been studied for more than a century. It is bright, well-observed, and seemingly straightforward. And yet, its age estimate has repeatedly threatened to break one of the most fundamental boundaries in cosmology. The universe is about 13.8 billion years old, based on measurements of cosmic expansion, the cosmic microwave background, and the large-scale structure of space. That number is not arbitrary. It comes from multiple independent lines of evidence that converge remarkably well. Stars, however, must be younger than the universe. They formed after the Big Bang, once matter cooled and condensed. No star should ever appear older than the cosmos itself. And yet, early estimates of the Methuselah star's age placed it at around 14 billion years, with uncertainties that overlapped or even exceeded the age of the universe. That overlap is where the tension begins. To understand why this happened, we need to look at how astronomers determine stellar ages. Unlike people, stars do not come with birth certificates. Their ages are inferred indirectly, using models of stellar evolution. These models describe how a star's brightness, temperature, size, and chemical composition change over time. By measuring a star's properties and comparing them to theoretical models, astronomers can estimate how long it has been evolving. For stars like the Sun, this process is relatively well understood. For very old stars, especially those with unusual compositions, it becomes far more challenging. The Methuselah star is extremely metal-poor. In astronomy, metals refer to all elements heavier than hydrogen and helium. These elements were forged in earlier generations of stars and spread through space by supernova explosions. A metal-poor star must have formed very early in cosmic history, before many cycles of stellar birth and death enriched the universe. That alone makes the Methuselah star special. It is considered a second-generation star, formed from gas that had been only lightly enriched by the first stars. But even second-generation stars should still be younger than the universe by a comfortable margin. The age estimate of HD 1.0283 relies heavily on precise measurements of its distance, brightness, and chemical composition. Small uncertainties in any of these quantities can translate into large differences in age. In the early 2000s, improvements in distance measurements paradoxically sharpened the problem. As the star's distance was refined, its intrinsic brightness became better constrained, and the models suggested an age that crept upward, not downward. At one point, the best estimate hovered around 14.5 billion years, with an uncertainty of about 800 million years. Statistically, this meant the star could be younger than the universe, but it could also be older. That overlap was deeply uncomfortable. Astronomers responded the way they always do, by questioning every assumption. One obvious possibility was measurement error. Perhaps the distance was slightly off, or the star's chemical composition was mischaracterized. Even small errors in oxygen abundance, for example, can significantly affect stellar age estimates. Over time, more refined spectroscopy and improved stellar atmosphere models led to revised values. These adjustments nudged the star's estimated age downward, closer to 13.5 billion years. That helped, but it did not entirely remove the tension. The error bars still overlapped the age of the universe. Another possibility lies in the models themselves. Stellar evolution models are extraordinarily sophisticated, but they are still approximations. They rely on assumptions about nuclear reaction rates, energy transport inside stars, and how convection operates in stellar interiors. If any of these assumptions are slightly wrong, especially for metal-poor stars, the inferred ages could be systematically biased. In this view, the Methuselah star is not a problem because it is too old, but because our models are not perfectly calibrated for stars formed under such primitive conditions. Refining those models could resolve the discrepancy without requiring any radical new physics. There is also the possibility that the tension is simply a statistical edge case. When scientists estimate ages, they report a best value along with uncertainties. Occasionally, a result will sit near a boundary and appear to violate it, even though the true value lies safely within acceptable limits. If we could somehow measure the star's age with infinite precision, it might turn out to be comfortably younger than the universe. The apparent conflict could be an illusion created by overlapping error bars and our discomfort with ambiguity. This explanation is mathematically reasonable, but psychologically unsatisfying. It feels like sweeping the problem under the rug. What makes the Methuselah star particularly interesting is how it mirrors earlier anomalies in a subtler way. Unlike Phoebus or Oumuamua, it is not fleeting. Unlike the cold spot or the Bota's void, it is not vast. It is a single, persistent object that sits right at the boundary of what our theories allow. It does not force an immediate crisis, but it refuses to go away. Every improvement in data seems to reduce the problem without eliminating it entirely. The star remains uncomfortably old. There is also a deeper implication lurking beneath the technical details. The age of the universe is one of the most important numbers in science. It anchors our understanding of cosmic history, from the formation of the first atoms to the emergence of galaxies and life. If even one well-studied star appears to challenge that number, it demands careful attention. So far, the consensus is that there is no true contradiction. The Methuselah star is likely slightly younger than the universe, and the overlap is a product of uncertainty. But the fact that we can even approach this boundary tells us something profound. It tells us that our measurements have become precise enough to test cosmology on the scale of individual stars. That was unthinkable just a few decades ago. In this sense, the Methuselah star represents both a success and a warning. It shows how far observational astronomy has come, while also reminding us that precision exposes tension. As our measurements improve, they do not always settle questions cleanly. Sometimes they sharpen them. Like many of the mysteries we have explored, this one ends without a definitive resolution. There is no dramatic revelation, no overturned theory. Instead, there is a lingering discomfort, a narrow gap between what we measure and what we believe must be true. The Methuselah star sits quietly in the halo of the Milky Way, shining steadily, unconcerned with the debates it provokes. Whether it is a statistical fluke, a challenge to stellar models, or simply a reminder of how hard it is to measure deep time, it remains a symbol of unresolved tension. After explosions that fade too fast and visitors that vanish into interstellar space, this star offers a different lesson. Some mysteries do not shout. They whisper patiently across billions of years, asking whether we are truly as certain about the universe's timeline as we think we are. Taken one by one, each of these mysteries can feel like a curiosity, an odd footnote at the edge of an otherwise successful scientific story, a strange signal that never repeated, a star that dims when it shouldn't. Rings visible only in radio waves, structures that seem too large, voids that feel too empty, a cold scar on the oldest light in the universe, a star that carries elements it should not have, an interstellar visitor that slipped through our hands, explosions that burn too fast to classify, a star whose age presses uncomfortably against the age of everything. But when you step back and place them side by side, a pattern begins to emerge. The pattern is not in the anomalies themselves, but in what they reveal about how we understand the universe. Again and again, these phenomena appear at the boundaries of our models, precisely where our descriptions of nature are stretched thin. The unifying lesson is not that the universe is broken or that science has failed. It is that our models are incomplete, and that incompleteness is not a flaw, but a feature of how knowledge grows. Science does not advance by collecting facts until the picture is finished. It advances by building models that work well enough to explain what we see, then revising or replacing them when reality refuses to cooperate. Every mystery in this series sits in that space of refusal. The wow. Signal challenges our assumptions about radio noise and the rarity of transient phenomena. Tabby's star challenges our understanding of stellar environments and large-scale obscuration. Odd radio circles challenge our catalog of cosmic structures. The giant arc and big ring challenge the idea that the universe smooths out neatly on the largest scales. The Bota's void challenges our intuitions about emptiness and structure formation. The CMB cold spot challenges our confidence in the statistical simplicity of the early universe. Przybylski's star challenges nuclear astrophysics. Oumuamua challenges our models of small bodies and interstellar debris. Fast blue. Optical transients challenge our classification of stellar death. The Methuselah star challenges our measurements of time itself. None of these anomalies, on their own, destroy the frameworks we rely on. But together, they point to the same conclusion. Our current theories are powerful, but provisional. This situation is not new. In fact, it is the historical norm. At the end of the 19th century, many physicists believed that the basic laws of nature were essentially complete. Classical mechanics, electromagnetism, and thermodynamics explained almost everything that could be observed. What remained, it was thought, were small details to be worked out. Then came a series of anomalies. The orbit of Mercury did not behave as Newtonian gravity predicted. The speed of light appeared to be constant regardless of the observer's motion. The spectrum of blackbody radiation refused to make sense. These were not dramatic failures. They were small discrepancies, confined to narrow regimes. But they mattered. They accumulated. And eventually, they forced a radical rethinking of space, time, and energy. The result was relativity and quantum mechanics, theories that did not just patch the old models, but replaced them with deeper ones. The old theories were not wrong. They were incomplete. They worked within certain limits and failed beyond them. Cosmology has its own version of this story. When Edwin Hubble first showed that galaxies are moving away from us, revealing that the universe is expanding, it overturned the long-held assumption of a static cosmos. Later, when astronomers discovered that this expansion is accelerating, they were forced to introduce dark energy, a component of the universe that we still do not understand. Today, dark energy makes up roughly 70% of the total energy content of the cosmos, and yet we know almost nothing about its nature. Once again, the model works extraordinarily well. It fits the data. It predicts observations. And yet, it rests on an unknown ingredient. This is the pattern repeating itself. Success does not eliminate mystery. It sharpens it. The anomalies we have explored belong to this same tradition. They are not signs that everything we know is wrong. They are signs that what we know is partial. The standard cosmological model explains the cosmic microwave background with astonishing precision. It predicts the large-scale distribution of galaxies. It accounts for the expansion history of the universe. And yet, it leaves room for features like the cold spot, like unusually large structures, like extreme voids. Stellar evolution models explain the lives of most stars beautifully, and yet they struggle with Przybylski's star. Planetary science explains comets and asteroids well, and yet Oumuamua slips through the cracks. High-energy astrophysics explains supernovae and gamma-ray bursts, and yet F-bots occupy an uncomfortable middle ground. These gaps are not failures. They are invitations. One of the most important drivers of these invitations is technology. Almost every mystery in this series exists because we learned how to see something we could not see before. The wow. Signal required radio telescopes sensitive enough to detect narrow-band emissions. Tabby's star required continuous, high-precision monitoring of stellar brightness. Odd radio circles required wide-field radio surveys capable of detecting faint, diffuse structures. The giant arc and big rings required massive galaxy surveys spanning billions of light-years. The Bode's void required three-dimensional maps of galaxy distributions. The cold spot required satellite measurements of the CMB with microkelvin precision. Przybylski's star required high-resolution spectroscopy. Oumuamua required automated surveys scanning the sky every night. F-bots required rapid cadence, all-sky monitoring. The Methuselah star required precise astrometry and refined stellar models. In each case, the anomaly was not predicted. It emerged as a byproduct of better observation. This is a crucial point. Science does not usually discover new phenomena by looking for them explicitly. It discovers them by increasing its sensitivity and scope, then being surprised by what appears. Every new instrument is a question we did not know how to ask before. Sometimes the answer fits neatly into existing theory. Sometimes it does not. When it does not, theory must adapt. This is why uncertainty grows alongside knowledge. The more we see, the more we realize how much we have not yet understood. There is also a deeper philosophical thread running through all of this. Many of these mysteries persist because they cannot be repeated or controlled. The wow. Signal happened once. Oumuamua passed through once. We have only one universe, one cosmic microwave background, one realization of cosmic history. In laboratory science, repetition is the ultimate arbiter. In cosmology and astronomy, repetition is often impossible. We are observers, not experimenters. We infer laws from patterns in what we see, knowing that those patterns are drawn from a single, unrepeatable history. This places fundamental limits on certainty. When something sits at the edge of probability, like the cold spot or the Methuselah star, we cannot simply rerun the experiment to see if it happens again. We have to live with ambiguity. Living with ambiguity is not a weakness of science. It is one of its defining strengths. Science is not a collection of facts carved in stone. It is a method for navigating uncertainty. It tells us what we know, how well we know it, and where the gaps are. It teaches us to quantify doubt rather than ignore it. Every unresolved anomaly is a marker of intellectual honesty. It says, "Here is where our understanding ends for now." That, for now, is doing important work. History shows that today's anomalies are often tomorrow's breakthroughs. There is also a lesson here about humility. The universe has repeatedly shown that it does not conform to human expectations. It is not obliged to be simple, tidy, or intuitive. The idea that our current models might be incomplete should not be surprising. What would be surprising is if a species that has been doing science for only a few centuries had already reached the final description of reality. When anomalies appear, they are reminders of our place in the cosmic story. We are not external observers standing outside the universe, looking in. We are part of it, trying to understand the whole from within. At the same time, these mysteries are not reasons for despair or cynicism. They are sources of wonder. Each anomaly represents a point where reality becomes more interesting than our expectations. They show that discovery is not finished, that there are still phenomena waiting to be understood, perhaps phenomena that will reshape our picture of the cosmos as profoundly as relativity or the discovery of cosmic expansion once did. They also show that curiosity is not something to be outgrown. It is something to be refined. There is a temptation, when confronted with unresolved mysteries, to jump to extreme conclusions. Aliens, multiverses, exotic new physics. Sometimes those ideas are worth exploring. Often, they are placeholders for ignorance. The important thing is not which explanation we prefer, but how we test them. Many past anomalies were resolved without invoking radical new concepts. Others required revolutions in thought. There is no formula for knowing which path a given mystery will take. The only reliable approach is patience, skepticism, and openness combined. Perhaps the most profound takeaway from all of this is that uncertainty is not the opposite of knowledge. It is part of knowledge. When we say we do not know what caused the wow signal, or what Oumuamua truly was, or why Przybylski's star contains forbidden elements, we are not admitting defeat. We are drawing an honest map of the frontier. Frontiers are where exploration happens. They are where questions are sharpest and assumptions are weakest. Seen together, these cosmic mysteries form a kind of mirror. They reflect not just the strangeness of the universe, but the nature of our attempt to understand it. We build models, we test them, we refine them, and occasionally, reality pushes back. When it does, we have a choice. We can ignore the anomaly, dismiss it, or explain it away prematurely. Or we can sit with it, study it, and allow it to reshape our thinking. History suggests that the second choice is the one that leads somewhere new. In the end, there may be no single revelation that ties all these mysteries together. They may have different causes, different resolutions, and different fates. Some may eventually be explained and lose their mystique. Others may remain unresolved for generations. That is not a failure. It is the natural state of a living science. The universe is not a puzzle with a final piece waiting to be placed. It is an ongoing conversation between observation and explanation, between what we expect and what actually is. As we look out into the cosmos, armed with ever more powerful instruments and ever more refined theories, we should expect the number of mysteries to grow, not shrink. Each layer of understanding peels back to reveal another beneath it. That is not a sign that we are lost. It is a sign that we are moving forward. The strange, the unexplained, and the unsettling are not interruptions in the story of science. They are the story, and in learning to live with uncertainty, we may be doing the most human thing of all, continuing to ask questions, even when the answers are not yet in sight. After walking through all of these mysteries, what stays with me most is not any single anomaly, but the emotional posture they collectively demand from us. They teach patience, they teach restraint, and above all, they teach humility. It is tempting, when faced with the unknown, to rush toward answers that feel satisfying, dramatic, or final. We are pattern-seeking creatures, uncomfortable with open questions. But the universe does not operate on our psychological schedule. It reveals itself slowly, unevenly, sometimes teasing us with clarity, sometimes confronting us with silence. The longer I sit with these stories, the more I realize that their true value is not in what they explain, but in what they refuse to explain too quickly. One of the most important lessons is that confusion is not a failure state. In everyday life, confusion feels like something to escape. In science, confusion is often the sign that we are paying attention. Every mystery we explored arose not from ignorance, but from precision. The wow. Signal was discovered because we were listening carefully. Tabby's star was found because we measured stellar brightness with unprecedented accuracy. The cold spot emerged because we mapped the cosmic microwave background down to tiny fractions of a degree. These anomalies are not cracks caused by sloppy work. They are stress marks created by pushing our understanding to its limits. That distinction matters. It means that uncertainty is not an enemy of knowledge, but one of its most reliable guides. Another lesson is how deeply our theories depend on context. Models are not universal truths carved into reality. They are tools built for specific regimes. They work astonishingly well until they don't. Newton's gravity did not become useless when relativity arrived. It became contextual. The same is true for our current cosmological and astrophysical models. They are not wrong simply because anomalies exist. They are incomplete because reality is richer than any single description. The danger is not in having incomplete models. The danger is in forgetting that they are incomplete. These mysteries serve as reminders that confidence must always be provisional. What also becomes clear is how much discovery depends on chance. Timing matters. The wow. Signal appeared once, and we happened to be listening. Oumuamua passed through our solar system just as survey telescopes became capable of detecting it. A2018 cow exploded in a part of the sky we were monitoring closely. Had any of these events occurred a few decades earlier or later, they might have passed unnoticed. This introduces a quiet, humbling realization. Our picture of the universe is shaped not only by what exists, but by what happens to cross our observational path at the right moment. There may be countless phenomena unfolding all the time that we simply miss. Absence of evidence is often absence of opportunity. There is also a deeply human tension running through all of this. We crave closure, but the universe offers process. We want answers that settle questions permanently, but nature seems to prefer layered explanations, where solving one mystery reveals two more beneath it. This is not a flaw in the scientific endeavor. It is its defining rhythm. Progress does not move in straight lines. It oscillates between understanding and doubt, between clarity and confusion. Every time we reach a plateau, the horizon expands. These mysteries are not roadblocks. They are signposts marking the edge of current understanding. What I find especially striking is how often these anomalies live at extremes. Too large, too empty, too fast, too old, too precise, too rare. Nature seems to probe the boundaries of possibility far more enthusiastically than our intuitions would suggest. And those extremes are where theory is most fragile. It is easy to build models that describe average behavior. It is much harder to build models that gracefully accommodate the outliers. Yet outliers are often where the most important information hides. They expose assumptions we did not realize we were making. There is also a lesson here about restraint. Some of the explanations proposed for these mysteries are bold and imaginative. Aliens, multiverses, new physics beyond anything we have tested. These ideas are not inherently wrong, but they carry a responsibility. The history of science is filled with ideas that were exciting, elegant, and ultimately incorrect. What separates productive speculation from fantasy is discipline. The willingness to say, "We don't know yet," is not a lack of imagination. It is an act of respect toward reality. Speculation without constraint is storytelling. Speculation anchored to evidence is exploration. Perhaps the most profound takeaway is how these mysteries reshape our relationship with certainty. We often think of science as a machine for producing certainty, but that is only half the story. Science is equally a machine for producing better questions. Each anomaly sharpens our sense of where understanding ends and mystery begins. That boundary is not fixed. It moves, but it never disappears. And that is not something to lament. It is something to appreciate. A universe that could be fully understood would be smaller, in a meaningful sense, than the one we inhabit. There is also something quietly comforting in this. The fact that we do not have final answers means that discovery is not reserved for the past. It is ongoing. The next generation of instruments will reveal phenomena we cannot currently imagine, just as current instruments revealed mysteries that previous generations could not see. The story of understanding is not winding down. It is accelerating, and we are living inside that acceleration, watching the universe become stranger as it becomes clearer. At a more personal level, these mysteries encourage a certain emotional posture toward the unknown. Curiosity over certainty, humility over confidence, patience over premature conclusions. They invite us to be comfortable not knowing, to resist the urge to fill every gap with an answer simply to relieve discomfort. That posture is rare, not just in science, but in human culture more broadly. Yet it may be one of the most valuable skills we can cultivate. In the end, what these stories offer is not a catalog of cosmic oddities, but a philosophy of exploration. They remind us that understanding is always partial, that knowledge grows through confrontation with the unexpected, and that mystery is not a failure of explanation, but its fuel. The universe does not owe us simplicity. It does not owe us closure. What it offers instead is depth, complexity, and an endless invitation to keep looking. And perhaps that is the greatest lesson of all, that the value of inquiry lies not in reaching the final answer, but in continuing to ask better questions, even when the universe responds with silence.